hello everybody. I'd like to extend a warm welcome to all of you as well. It's nice to have you all here in such numbers at NewStore in our new office. It's a great first start to hopefully many more presentations to come, which Goran will introduce at the end of the session. What do we do at NewStore? We provide services and applications that help retailers to provide a shopping experience to their customer base that is up to par with what they expect anytime, anywhere, and with single-touch simplicity. We use obviously many technologies that Mitchell has built and provides, maybe Terraform or Consul or Packer or Vagrant. So we are a real fan of his work. And we provide microservices in Go as well as in Python, and front-end technologies like React Native and Swift. So if you want to know more about us, there is plenty of people from NewStore here attending, and feel free to talk to them afterward. And without further ado, I'd like to give the word to Mitchell.
Thanks. Hello, and thanks NewStore for having me. So if you've ever seen me give a talk before, I usually like to move around, but I hurt my knees a couple days ago, so I'm actually gonna sit on this high stool, so hopefully everyone can still see me, but it's not very uncomfortable to actually stand for a long time. So I'm just gonna sit down now. Yeah, that's a lot better. Feels a lot better. All right, so today I'm gonna be talking about advanced testing with Go. We'll get into it, and this is not going to be, probably you'll be happy to hear, this is not going to be an abstract talk in any way. It's going to be very much method, code sample. It's going to be a lot of exactly how we do things. So let's just sort of get right into it. I think it's this button, I guess. Yeah, so I got a good introduction, but also my Twitter handle, if you wanna ask me a question and I'm not here, or you can't get to me, or you're shy, it's all fine. Just tweet at me, or you could find my email through there too, and just email me and I'll answer it for you. And so I work for and started a company called HashiCorp. If you hadn't heard about it, that's totally fine. We've created 9 tools to date. 8 of them are open source. These are the logos for all of them up here. In order, I'm just going to name them. I'm not even going to tell you what they do. You could look them up if you're curious. But in order of this slide, it's Consul. Oh, I have this. It's Consul, Terraform, Vault, Surf, Vagrant, Packer, Nomad. Atlas is our commercial project, and then Auto. And of these 9 tools, 8 of them, these 8 on the outside, all of them except for Vagrant, are written in Go. So we've been doing Go a long time. We have written a lot of lines of code in Go. I did a line of code count like a while back, and I think that all our projects put together are a few million lines of Go. So we've written a lot of Go, and we've learned a lot. So that's what I want to talk about today. And so a little bit about our usage of Go. So it's been our primary language for everything for 4 years. 4 years ago when we started using it, I think it was Go 1.0 actually had come out. 1.1 wasn't out yet. And also the community was really, really young. So there wasn't a lot of libraries, there weren't a lot of users, there weren't a lot of questions, and actually a lot of like the Stack Overflow that you would find would be wrong, just from the perspective of it was written for like Go betas or something. So it was sort of rough then. It's really good now. And of course, every Go release just keeps getting better and better, and then the community keeps growing and growing. Like Go4Con, I think I went the first year and it was like 300 people, and then last year it was something like 1,000 or something. It was something crazy. I'm sure this year will be crazy too. So. The software we write is in use by millions. We get millions of downloads, and more importantly are the smaller numbers but the bigger companies. So our software in particular is used in a lot of very, very large companies. So think data centers of thousands of servers, think number of data centers in the dozens. And that sort of scale. So we sell, those are the people we make money from, those are the people we sell to, so we have to make sure our software works well there. And the various types of software, right? So we've written multiple sort of paradigms of software. I mean, we have distributed systems, we have desktop software, we have security software, and others. But based on these paradigms, there's certain properties that are really important. So correctness in general is pretty important, but correctness of something that works in production that's in the path of downtime, or correctness in terms of something that if it ever leaks data insecurely is a complete failure or potentially a legal issue of the system, is stuff we have to worry about. And so we test very, very heavily. As an example, with Terraform, the number of test lines of code to the number of regular lines of code is 10 to 1. The number of tests covering a single feature is usually in the dozens. So we don't, I sort of talk about it later, but we don't test at one layer. I believe in sort of testing it at every layer so that even if someone refactors and happens to remove a test, they'll still get caught. So we'll get to talking about that, but dealing with all these different kinds of software, bringing it up, lets us see a lot of things. And I thought the next slide had it, but let me get to it. So ignore my hand. So basically, there's two parts of testing I'm going to talk about today. The two parts are test methodologies and writing more testable code. And they're two separate things, but all one and the same towards the same goal. So for this talk, this is actually going to be the slide style. If it's a black background with white text, it's going to be a test method. If it's white background with black text, it's going to be how to write more testable code. And the reason this is an important distinction is, well, again, I was wrong with the slide, but okay, so test methodology is going to be basically methods of writing tests. It's going to be techniques to write better tests, code samples of how we test certain things, and really testing is a whole lot more than do something and assert something happens. At a very generic, like high level, that is what testing is like do something and verify something happens, but a lot of how to test, or introduction to testing is a lot of, call a function, get its return value, assert that the return value is something you expect. And you will write that a lot, but to actually fully be able to test code and test these weird cases, testing ends up actually becoming a lot more than that. And then for testable code, it's just as important as how you test it. So a lot of developers, especially new hires at HashiCorp that we talk to, will write something and I'll ask for the tests. And they'll say, oh, I tested part of it, but I didn't test all of it because you can't. And then I look at it, and they're not wrong that they can't test it right now, but they're only wrong because you can't test it because of the way they wrote it, not because the actual concept itself can't be tested. So basically, writing testable code is an important thing that I'm actually putting together another sort of slide deck on that I want to give internally at HashiCorp, which is about this, and it'll include a lot of the stuff I talk about here. And a lot of it requires rewriting components or large sections of your code, which is really, really painful, but generally worth it due to the stability you get out of it. Okay, so let's get right into it. So we're diving right in, and we're going to start. They're sort of in order from simple and things that you probably know to more complicated things. I imagine there's some pretty advanced Go users here as well as beginners. If you're a beginner, most of it might be new. If you're an advanced person, I hope and expect that at least one thing you see here is pretty new. We have some pretty advanced Go users, Go programmers at HashiCorp, and I showed them the deck today, and all of them found something that they didn't know. So let's do it. Okay, so table-driven tests. It's one of the first things I found in Go. I didn't invent it. It was well known before I even came to Go. It's used in the standard library a lot, and it's still to this day is one of my favorite things. So a table-driven test looks like this. And it's called table-driven because what you do is at the top of the test you make an array of cases, and it looks like a table. So it's table-driven. And then for the test itself, you actually loop over all the cases and test each case. And that's all there is to it. So in a single test that you're writing in Go, so it's just a single test case, you have multiple cases. And in something like Ruby or a dynamic language, you might actually put these cases outside and generate multiple tests for it. That's a cute thing to do. But in Go, you don't really have to do that. So it could be a downside for you, it could be an upside. I'm not making an opinion either way, but this is sort of how you do it. This is done in the standard library a lot. A lot of times people will pull out this table and just make it a global variable. That's fine as well. But this is a table-driven test. And the key points for the table-driven test is it makes it very, very low overhead to add new test cases. And the example I showed before is, there's not much going on, we're just adding a number, but imagine a test case that had a lot of setup and a lot of teardown. If you were to write new cases without using a table, you would have to duplicate that setup and teardown multiple times. And even if you pull it out into a function, it's just a lot of boilerplate for each test case. And the main benefit of that is just being able to add the new test cases easily, which is important for bug repros and things like that. So a lot of times when we get a bug in Terraform or a bug anywhere, the first thing I do is try to find the table that tests that. Sort of another bullet point is follow this pattern even for single cases. So even if we write a test for the first time that we can't think of any other cases that would ever require a table, we just make it table driven anyway, because when you get a bug, you just want to be able to really easily see if you could repro it by putting a case in a table. That's a lot easier than rewriting a bunch of boilerplate. So that's really the first step for us, is add a case to the table. If it fails, then super good. Now we can start working on the bug fix. Otherwise, we keep looking, basically. So do this pattern a lot. We do this in, I would say, at least like over half of all our test cases for our projects are table-driven in some form. And again, like I said, a lot of the tables will just be one case because we haven't found a need for another case yet. But adding the 10 or so extra lines per test that are required to make it table-driven are worth it for our longer-term maintainability. As an aside, consider naming the tables. So the one before was a slice of cases. If you make it a map with a key, you could actually just name it, and the only thing that key is used for is the error message if it fails. This is not something I did and not something the standard library does, but as we started hiring more engineers to work on projects they hadn't worked on before, and they started working on features where they were getting test failures, having error messages with just the inputs or an index was really, really hard for them, especially because we do have some table-driven tests with hundreds of cases. So when it's like failure at index 62, you actually open the text file and you start going 0, 1, 2, 3, 4, and it's really sad. So we still have a lot of. I use the array one still, or the slice one still, for very small tables or tables where the inputs just tell you enough where you don't even need to look at the case. But for anything more than a handful, I try to use this. Which is surprisingly, maybe just me, but surprisingly annoying to start doing, but pays off for, again, maintainability later. All right, next method, so test fixtures. Looks like this, and the key is using just a relative path to get a test fixture. So that looks really simple. Surprisingly, not a lot of people know this, but go test will actually, no matter where you call it from, will change directory to that package. So your working directory in every test case is always the package directory. So that means you could actually use relative paths to access test data. And so our pattern is to always use this test fixtures directory, and we usually actually have a helper, which I talk about later, but we usually always have a helper so that you could just give it like this name and it puts the path together for you. We always use test fixtures for all our test data. So I use the word fixture, which might mean something if you're like what came from a web framework or something, which is like mock data. But when I say fixture, I mean basically anything. So anything the test might need to run. So this could be fake configuration. It could actually be fake data. It could be expected outputs. It could be runnable binaries that it's testing. It could be a lot of things. Basically anything it needs that isn't Go code for tests, I throw in this directory. It's always relative to the package, which is really nice because no matter what package you go to, you know that it's always in this directory, and it's easy to use. So test fixtures, that's all there is for that one. The next pattern is something that the most common case I see it is what I'll call golden files, but the more abstract thing I'm showing you here is the ability to add new command line flags to your tests. So golden files, this example I just wrote for this slide, but this is a pattern that again I got from the standard library that Go uses. But it's a pattern that now that I've figured it out, I use all over. So the idea with golden files is to instead of testing the output of something to something in code, like if the actual value equals this thing I hard-coded, you actually are reading the output from a golden file. So you read the output from the file and you compare it to the file contents. And then the other key is that you have a flag that you declare globally. In the standard library, it's always called update, so I've continued the pattern of calling it update. And if you run it with the update flag, we'll actually, before it tests, update the golden file. So update will always make anything that uses the golden file to make the test pass every time, but the point is that it updates the golden files. And the use case for this is actually for things that are hard to compare against. So imagine you have a really complex data structure that you can't deep equal compare for various reasons, that it just has a few subtle differences, and you're trying to figure out what you're supposed to do. One way we do this is actually implement a string method on it, or even a private, like unexported test string method on it. Have it output a bunch of stuff, and it could be like kilobytes of output really at that point, and we just compare that output to a golden output. So you're actually comparing complex objects without having to hard code that complex object in your test file. And so the way the reason the Go standard library uses golden files is actually to test the printer. So when you run go fumpt, the formatter, the way that go fumpt is unit tested is that it has a bunch of golden files. So the input is some really ill-formatted Go code, and the golden output is the formatted Go code, and that's the way that they run unit tests. So they run update whenever they choose the fumpt, whenever they change the fumpt package, but if they're not changing it, they run it without the flag, and if that ever changes, then there's a problem. So that's why fumpt will never break for you. So that's where I found it. We also use it for printer testing, for our configuration language and things like that, but we also use it for complex objects. So it just looks like this. You could run go test and it'll actually test the outputs. If you pass the update flag to the test, it'll actually update the thing. So the more abstract thing here I'm showing you is that you could actually add new command line flags to the go test command by making them global as well. So we do this for another thing we saw in the Go standard library, which we use this for, is a slow flag. So if there's certain tests that test something that's already tested somewhere else, but with a lot bigger input. So we have, I have this personally, I have this one library that actually parses really complex log files that are megabytes large. I have fast ones that as the input gives it, kilobyte-sized things, so that the Go test happens in milliseconds. But for complete testing, I actually have a slow flag that also loads in dozens of megabytes of real, full, complete logs and tests against those. But when I'm iterating on something, I don't want the test to be slow, so I have a slow flag for that. But you can do almost anything with these flags, and we actually use these flags in a really, really clever way towards the end, towards one of the more advanced concepts. We use these flags in a way that you've probably not seen, that I've never ever seen another project do except ours, even though again it's from the Go standard library. All right. So golden files, test complex outputs. You human eyeball the generated output. I guess I didn't mention that. So how do you know if it's so much output? How do you know if it's changed? You're version controlling. So the way I check is just git diff. So I run it with update, and then I git diff and actually look at the line differences. So that also encourages you to make the complex object output line based, so that git is useful. But the idea is that hopefully you're not changing the test so that you're like full golden output, which could be huge, is changing. Hopefully you're changing the implementation in a way that only a few of it's changing, and you're making sure that the changes are right. So that's the risk of golden output, is obviously you have to eyeball the change and make sure it's correct. But still, to me, a lot easier than like hand typing a bunch of stuff. And yeah, it's very scalable to write a thing. And so, like I said, you can write a string method. A lot of the times, and the way the Go doc says is the string method is for human readable output of your object. And if you don't think that your test output is human readable, or you want to include data that's private that the user of your package should never see, what we do is actually implement a method called test string, where test is a lowercase t, so it's never exported, they can never call it. The idea is the same as string, except the output is only supposed to be used for tests. But a lot of times, like in Terraform, we do this, and a lot of the times the string output is just what we'd want to test anyway. It's enough. Okay, so getting to how to write testable code. The first one, so again, probably simple and obvious, is global state, or the lack of it. So the idea with global state is to not do it. So avoid it as much as possible. Global state makes writing tests really hard because you can't really mock the global state or affect it. So there's a lot of ways, and it makes races a problem. So what we recommend, or what we try to do, is the best case is to not use global state at all. But if you want to use global state, the reason you're usually using global state is for some sort of config that rarely changes or something. So make it a var, not a const, so that the test actually could edit it. Is a better approach. The other reason we see global state usage is memoizing objects. That's okay as long as you provide a function. Again, it doesn't have to be exported, but as long as you provide a function to clear it, so that the test could actually clear it, so you're not having one test poison the next test with its global state usage. But basically, here's the idea. So this is a really terrible idea. Like, yes, port is a constant, so the motivation for saying constant port is a good one. But if we can't modify that port for a test, it's a big problem. So constant's fine if there's another way to modify the port. That's fine. So it doesn't have to be this. This is a little bit better because at least we can modify it. It's not exported, so only we're modifying it. This is the best, where it is a constant, so like you feel good about yourself, but you could actually modify the port in some other options, and that's really important for tests. So with global state, if you're ever using a global var or const, just think about, can tests modify this in some way? All right, so the next method is test helpers. So it's starting to get a little bit more advanced. And I think that the idea of a test helper is going to be obvious to you, but the way I show you, a very unique way that I show you to use test helpers here will probably be new to you. Okay, so test helper, we use them a lot, and here's a test helper that creates a temp file, and the Go standard library gives you a method for generating a temp file, so the question might be why we want a test helper. Well, by making a test helper, we're able to make temp file generation 1 line versus 7 or 6 if you remove the white space and like ugliness. So the helper gives us a way to make a temp file that's 1 line versus 7. And why that's important is I actually personally don't care about dry. Like the concept of dry, like I'm not one of the dry zealots. Like I don't care that much. But what I do care about is that when I'm looking at a test case, knowing what it's testing. And when you have a lot of boilerplate setup stuff for mundane things like getting a temp file or copying a directory or something like that, it takes away from what's actually being tested. And so usually when I look at code I haven't written or code that I'm changing, I always open the test next to it to be like, okay, what's the behavior of this that I'm trying to not break? And of course the test will tell me if I break it, but I also want to understand. So I'll go look at the test, and if the test is 50 lines of setup and 50 lines of teardown, and there's 3 lines of assertion in the middle that's actually testing behavior, as a first-time person approaching that, I will read all 100 lines because I don't know what's important and what's not important, and that really sucks as a new developer coming onto a project. As an existing developer, if you're happy copying and pasting boilerplate, like totally fine with me. This isn't for the existing developer. It's really for the new one you're hiring onto a project or bringing onto a project to help them out. The other thing is that you pollute your test with a bunch of error checks, which again this error not equal nil assertion thing here is not what that test is testing. You need to have that assertion there because if you need a temp file and creating a temp file fails, and obviously the test should fail, but putting that assertion into the actual test, again, is confusing because I don't know if that's what I care about. So if you put it out in a temp file for a helper, specifically for test, the really cool thing is you can just pass in the test parameter, and that could still cause failures of your test, but at least you're hiding those assertions that don't really matter and probably won't happen. Like this, I don't think I've ever seen temp file creation actually fail in any of our test cases over 4 years. But you still need it there because if you underscore that error, the day that the temp file creation fails will be so many hours of expensive developer time lost just realizing that you ignore that error. It's not worth it. So you do want it there, even though it's probably not going to happen. So this provides you a way to do that. and this isn't the thing that I think that like the advanced users will have never seen that's coming up, but test helpers, we use them a lot, they're really important. And the key thing is test helpers should never, ever, ever return an error. There's no point. You get passed in the testing.t object and fail yourself. So if you have an error, just fail the helper. The real benefit of not returning errors is the usage is a lot prettier. So you could actually just like, if I needed a temp helper, a temp file for a configuration to a struct, instead of making it multiple lines where I call it, check for the error, and then configure the struct, now I just make the struct and put it right in the struct field. It's not important to the test, so I don't need to like separate it out or make it all pretty. I could just put it directly as the value of the thing. It's probably not going to fail, so I'll get my direct value out of it. Also, you could chain test helpers this way a lot easier. And I talked a lot about this last point. So that's that. Now here's the thing that I don't see often. I've only ever seen HashiCorp projects do this. I've not. That's not to say it's not out there. I'm sure it's out there somewhere. I've not seen this in the standard library, but something we started sort of in the past year is changing our helpers to actually have this pattern. So for things that need cleanup, we actually change the value to return what you want, and then just a function. And the function is actually just a closure to do the cleanup. And the reason this is awesome is because it turns your cleanup into just whatever you want. So you could actually defer the func, and as the test, you don't care what that func's doing. It's just like it's a cleanup of some sort. And if it fails, you could close over the testing thing. So if I was actually testing for errors here, which you always should, I just didn't because I ran out of space. If I was testing for errors here, I could do if error not equal nil t.fatalf and still fail the test, even though I don't have to pass it in again. I'm just calling the function directly. This gets even better if you don't have to actually return a value, if you're doing something with a side effect or for the purpose of a side effect. So this is a real helper that's in most of our projects, is test.chdir, which changes the directory for the duration of the test. And this just returns a func, so it changes the directory, and then the cleanup is to change back to the old one, so we go back to a clean state. And the cool thing is you could do this all in one line. You could actually call the test helper, defer the value, and the way that defers work in Go is it executes all of this and doesn't execute that last function call until it defers. So we actually get the behavior of changing the directory, and then we defer out later. And we do this a lot too. And again, I should be checking for an error here and failing with a test. And we do in our actual helper, but not for my paste here because I was out of lines. And I'll admit that I'm not, even though I was a Ruby programmer, or maybe because I was a Ruby programmer, I really despise magic. Like, I really don't like things that aren't obvious. And I will admit that this is not obvious what is going on. But also, if this is only for tests, I don't really care that much. It's not doing something evil. I'm not doing something magic for the purpose of doing something evil. It is actually pretty straightforward Go. There's nothing fancy happening here, and really the behavior is never going to affect the test. It's never going to affect the test. So it's something we do a lot, and this is again important because chdir is actually one that used to get on my nerves a lot. And the reason is because to actually effectively change directory and then change back at the end of a test, the number of lines you code you need to do that is like 15 or something. I didn't just count this. Like, if you asked me on the street, like before I ever made this deck, how many lines of code you need to change directory and change back, I would have said 15 really quickly, because I used to virtual yell, like not in a mean way, just in a personally upset way in our Slack channels about how dumb it was that you need 15 lines. And not because you need 15 lines to do it, but because this is so noisy for something that doesn't matter, like, to know. For a test, if you need to be in a certain directory for a test, having 15 lines dedicated to changing your directory and then 2 lines dedicated to testing something about that behavior is a complete waste of cognitive, mental, space when you're trying to figure out what that test does. So we made this helper real quick, figured that out real quick, and now it's one line that's usually at the top of the test like this, because the test is testing something to do with directories that's important. Most commonly for us, it's like CLI behavior. We're testing CLI behavior that's directory dependent. And we can put it right at the top. It's obvious that we're changing a directory to this, but all the other crap that sort of comes with changing a directory, that doesn't matter for the test, we don't need to worry about it anymore. And it's still one line, which is really nice. So returning a func for cleanup is a really nice, elegant way to do cleanup. I see a lot of test helpers out there that do return things like I/O closers. That's what we started with, is we would create custom I/O closers that the defer would always be thing.close, which is a very Go idiomatic way to do things. And it feels nice. Like we would even create a I/O closer implementation for changing back to the directory that you were supposed to. And that feels nice, looks nice, and if this was not test code, that's probably what I would do instead. But because it's test code, we can make this a lot nicer, we can make it look a lot nicer, and this is sort of a neat trick to do that. And the one that I would imagine that most of you would need in some sort of like library or something is probably test.chdir. That's probably the one the first one this comes up in. All right, so that's test helpers. A lot more test helpers than you probably thought. All right, so again, writing testable code. So package and functions. Actually also a really complicated thing if you're new to Go in general, like outside of testing. So for package and functions, use them is really what this whole section's about. But break down functionality into packages and functions and do it a lot. Don't be afraid to do it. The note here, which is really hard, and this is what's hard for beginners, is to don't overdo it, which is a very qualitative thing for me to say. I'm not saying that if you do X, it's overdoing it, but if you do Y, you're still good. I'm not giving you a formula for how to not overdo it. So you just kind of have to do it until you figure out what that means. And that means making mistakes, but that's what's going to happen. Or working with someone more senior than you that sort of teaches you a practice for doing it. When we first started, like some of our original Go that Armand and I wrote, even Packer, actually to this day, like the current organization of Packer right now, I'm really unhappy with, just because I didn't really know the proper way to break down packages and functions. But the general idea is sort of each unit of functionality, unique functionality, is a separate package. And functions, I think we all know. I mean, if you're a developer, you know how to break down functions. That's not weird. And for testing, unless the function is really complex, like as a general measure, not a hard rule, but unless a function is like hundreds of lines of code, which itself is a weird thing, but unless the function's really complicated, we only really test the exported interfaces out of packages. And the reason is because I view unexported things as sort of a means to an end of enabling the exported things. The unexported things are clearly only there to make the exported functionality work, because if you didn't need it, they wouldn't be there, and no one else could call them. So it's clearly there for only that reason. Go doesn't have the concept of like inner packages that could access the privates of outer packages or anything crazy like that. So unless the code directly in that one directory is using an unexported thing, then it's useless. So just test the code that's exported. And this is a fine line. I've met people, we've hired people that have this mentality at the bottom bullet point, which is that's sort of a somewhat black box approach to unit testing, where the black box in our case is the package. And I've met people that go down the road of the only testing that actually matters or is most effective or is most time efficient is to actually black box test the whole thing and let the whole insides be a Wild West. And I've thought that at various times in my career, but at this point we're pretty against that. So we test in layers, which is really important. You should black box test as well as unit test your packages, but we also unit test all our packages, but we do draw a line in that we only test the exported interface out of our package. The only difference here is if the unexported thing is fairly complicated, we will test it. So if there's a struct that does a whole lot of things that's unexported, that's really only there to support the external, we will unit test that, because the problem with the black box testing approach is when something fails, you'd like to know what failed, and when it's a black box test, you know something failed, which is nice. That's the reason that black box tests are nice. The reason they're not nice is because the thing that could have failed could be hundreds of lines of code. So then now you're on a println mission where you're like printing lines everywhere to figure out what went wrong. And you really want more granularity than that faster, and that's what unit tests give you. So if my exported function is using a struct to maintain state and do some fancy stuff, but that struct has multiple functions that have like dozens of lines each, so in total that unexported thing is hundreds of lines of code, I will unit test that unexported thing just for the purpose of finding a bug faster, or not introducing a bug when I change that thing. Yeah. I guess, I don't think I mentioned anywhere else. So I should mention here, and I really wanted to add this section before I came here and I just forgot. I have a very strong, and I don't think it's that common because I push it on almost everybody that starts at HashiCorp for every project, but I have a very strong test everything at every layer approach. So I'll give you a specific example. Terraform, it's a tool for modifying infrastructure. Terraform, when we add a feature to Terraform, the internals of Terraform is basically, it generates a graph, a directed graph, it executes the graph, it changes some state, and then it outputs to a CLI, let's say. And there's inputs to a CLI at the very beginning. Those are basically the steps of it. So when we add a feature to Terraform, the feature usually is a way we execute the graph. So in the core, we write a test for, did the graph change in the way we wanted it to? When we executed the graph, did the right thing happen? And I think a lot of people would stop there. And again, I've had this mentality before, and I've since changed course, which is that the perfect unit test is the unit test that perfectly tests that function in the most specific point possible. And that test, in my opinion, needs to exist, but you should also test it in every case that's then using it. So we'll write the test that tests the actual graph manipulation, then we'll write the test that actually sends input to the CLI in code, sends input to the CLI that exercises that graph execution and asserts the right output, and then we'll write a final acceptance test on the end that doesn't run within the code, but is actually sending input to the CLI installed on the machine, executes it, and asserts the output. And so Terraform has the practice of when you change one line of code, something like 20 tests fail. And the downside is it is hard to figure out what's actually the thing that went wrong because you're affecting so many things. Once you know Terraform, it's not too hard because you'll know sort of how the code flows and you'll be like, well, this is the package that's most specific, so it's probably in here. But the benefit here is avoiding inadvertently breaking something at another layer. So the example is the core might work, but maybe you didn't pass the right flag to enable that feature in the core from the CLI. So assuming you did, then it works in the CLI, but you need to test that as well. And so you're sort of testing these different things where you never thought that changing one layer would ever affect something so core, and it usually doesn't. Again, like most of the time it doesn't. And that might be a fair trade-off for you, but for certain projects, for Terraform, like Terraform a bug in Terraform could, and you should still use Terraform despite me saying this, but a bug in Terraform could straight up delete your whole infrastructure. So cutting lines of tests for the purpose of purity or the purpose of we tested it enough is not good enough. Like, if you can test it 10 times and the test code's identical but in 10 different packages, just go copy and paste that test code 10 times. I don't care. I'd rather have something fail super loudly for anything than to have a risk of slipping through. And that's our view on Terraform. Other projects don't take the same view, but I'm a big proponent of test the layers, test all the layers, every time. And that's why Terraform has so much test lines of code. Okay, that's my thing on that. Okay, so networking. Starting to get a little more advanced with networking stuff. So if you're testing networking, then make a real network connection. Netcon is an interface. And usually new users to Go, I actually probably put the interface section before this, but interfaces are nice because they make a really good mocking point. They're a point where you could slide in a custom interface to change the behavior. And so I actually see a lot of Go code, beginner and advanced, and libraries out there that are out there for mocking netcon, for making an in-memory netcon that you could control the flow of things using byte buffers. And there's just no point. There's no point in doing this. And the reason is because you could just make your own real TCP netcon, all not in memory, but local, with one helper, which is this. So here's a helper that we actually use in a lot of our projects of creating a client and server netcon. We basically create a listener on any port the kernel has open at the time. IPv4 is actually surprisingly important because we used to do just :0 and being like, we don't care, just let the kernel choose whatever it wants. and on some system configurations for firewall reasons and so on, that just fails. So for tests, like, I'm supportive of supporting IPv6 everywhere, but for tests, it's like, okay, let's just hard code it to IPv4. But anyway, yeah, so choose a thing, make a listener, in a Go routine, because some stuff has to happen in parallel here, actually have the listener accept a connection, and we're deferring that it closes, so you don't need the listener to be alive to keep your connection alive. So once the listener accepts the single connection, it's a test, so and for this case, it knows it's never going to receive another connection, it doesn't need to stay alive. Why burden the caller closing it? So the moment it gets its first connection, just close it, set it on some things, and then net dial, call it. This won't return, for TCP, you know, that won't return until the connection's fully established, so you know that this Go routine ended. For other things, you might want to use channels. I didn't want to complicate this example more, but net dial that local address, and now you have a non-mocked, fully controllable netcon. You could send any data you want on that, you could receive any data you want on that, and so there's really just no reason for ever using a mock netcon. You could, I mean, if you're testing really low-level networking stuff where you're trying to send corrupted packets or really wacky like window sizes or something like that, then maybe you need a mock netcon. But for real server software, like we never need to test that. We do need to test cases where what happens if we call the sequence of functions and then the server unexpectedly closes the connection or something like that. But you can do that with this because you have the server connection, so just call the thing and then at some point just call close. You could sort of, as a poor man's fuzzer, you could sort of fuzz things in a way of just looping over code and then random timings, just closing the connection and making sure that you're getting the right behavior. I don't know. You can do sort of whatever you want, but it's really easy to do. And that was a one connection example. It only allows one connection and then gives you the netcon and gets rid of it. It's easy to make that an end connection. It's easy to make that return just a listener on any port. We have helpers in a lot of projects. It's like, I just need a TCP listener. I don't care what port it's on or anything. Just give me a TCP listener. And that's just that first line of code, basically. It's easy to test any protocol, so we do this for UDP, we do this for Unix domain sockets. And it's easy to test IPv6 by making that 127 the IPv6 loopback address instead. So why ever mock a netcon? You don't have to. Okay, next, write testable code, configurability. Make everything configurable. If there's anything that's not configurable, it makes it a little bit harder to test. And sometimes it doesn't matter because your test's not going to change it anyway. But when it matters, it's really frustrating to change code. And maybe, in some cases, maybe it doesn't matter for you, but someone testing code that depends on your package actually needs to change something for their test. So make it configurable. If it's something you know never, ever, ever has to be changed, make it configurable and make it unexported so that the only person that can change it is your test. That way no one else will ever change it. But the important thing is go big on configurability. And so basically, like most things that are configurable have like an options struct, or the struct itself is the options. Make this long, document it is important. Like even if it's non-exported, doesn't mean you shouldn't document it. Document it for your own employees, your own testers. But just have a bunch of things in there. Any timeout, any ports, any file paths that you would use, make those all configurable because it's really important. That's all there is. And now we'll talk about why configurability is important in the context of subprocessing. All right, so subprocessing is always the one that people come to me and is like, I can't test that. It's usually a weird networking thing or it's subprocessing. Those are the two things that when I say why isn't there tests, the developer will say, oh, I can't test that because it's subprocessing to Git and I'm not going to mock Git's behavior and all this other stuff, which is very reasonable. But if you write your code the right way, it's all testable. So you have two options basically with subprocesses. One, you could actually do the subprocess. Make sure your unit test is a little weird because they're executing other programs, but it's there and it actually is, we do it and it's important. The other thing is to mock the output or behavior, which is sometimes hard, but again, you could do it. And so let's go over both. Subprocessing, where you're actually executing the real thing. So in this one, just execute whatever you need to execute. The example is we have a download library that one of the ways it could download things is using Git by Git cloning and manage. It's sort of like Go Git. We have a library for doing stuff like that. And those unit tests actually execute Git against a local repository and test all the edge cases of what happens if you download while you're on a branch, what happens if you download while you have stage changes. We actually test all that stuff by actually executing Git, because what I said earlier is right, which is you don't want to mock Git's behavior. That's actually really hard. In this case, the only important things are to guard the tests for if Git doesn't exist. So either fail quickly if Git doesn't exist so that the failure isn't more obscure, and also to make sure that your side effects don't affect anything. So in Git's case, we might actually be changing branches and stuff. Git is a stateful program. So what we do in our tests is make sure that we always copy the directories to a temp directory, like copy the .git folder to a temp directory and chdir and work on that temp directory to make sure we never side effect any tests, because I forgot about that when I first wrote it, and we actually had a bug where the first time you ran the test they passed and the second time you ran the test they failed, which is funny, but it's just because we had side effects outside our process. And so the way I usually guard for this sort of thing is this. So I make a global variable, and in the init process of in a test file, I actually just look for whatever we need and then flag whether we have it. And then in the tests that actually test things, I have a line, and this whole thing's actually copy and pasted from this library I've been talking about. And for this library, we test Git, we test Subversion, we test Mercurial. It's not a test failure if you don't have Git, so we just skip the test. It's not that big of a deal. We do log, though, that is not found. So that's sort of how we view it, but in this case, we actually do the subprocess. And that way, we've fully tested the subprocess behavior because we can execute that thing with the prerequisite that you install it, and we're not going to do that for you. Another example where we subprocess is we actually have, what test is it? Vault. So Vault, one of the backends that could use is Consul. And to test the Consul data backend, we actually subprocess and start Consul and bootstrap it and stuff all in the test, and then actually have it read and write to Consul, because the unit test otherwise would be all knocked down and it's not really testing that much. So we actually run it. So you can do this with pretty advanced things. All right, the other option is to mock execution. And in this case, I actually I always still execute a subprocess, but the subprocess it's executing is the mock. So exec command is the way you subprocess in Go, and it's not an interface, which is really annoying to me sometimes, but it's not an interface. So instead of wrapping it in an interface, I just accept it and just make the actual thing it's subprocessing to my interface. So I actually found this, again, in the standard lib, and I've never ever seen it anywhere else. But we use it to test our plugin infrastructure, which is all multi-process. We actually also use it to test some weird networking setups by subprocessing, having that thing make a weird network that's actually going over networks and doing stuff. So the way it looks like, this is going to be 3 slides because it's kind of complicated. But the way it looks like is this, and this is almost directly copy and pasted from the Go standard library. You have this is a test helper. By the fact it looks different than any other test helper you've seen, you sort of know I didn't write it. It's from the Go standard library. What this test helper does is creates an exec command instance, which is actually going to call back into itself. We're going to call back into the same process with some flags and some mvars, and those are important for a reason. I'll give you a second to understand. It's not complicated, it's just like, I think you'll read it and not know why any of this exists, which is fair because you don't know. But basically, we're calling this from a test, so we're making some new args. The new args are saying to run only a single test. Then we have this dash dash, and then we append anything we give to it, and we'll cover the importance of that later. And then we set an mvar go on helper process. If you Google this environmental variable, you'll find the source code in the Go standard library where it comes from, or you'll find our source code, because I haven't seen it anywhere else, like I said. And then you make the actual command, which is osarg0, so we're re-executing the same process in a naive way, but I've never seen this fail. Like, you could make this fail if you execute something with weird aliases and stuff, just don't. So osarg0, append the args, and set up the env with stuff. Okay, so that's how you make a helper process. Now let's see the receiving end of it. So on the receiving end, we actually write a test. Like this is a test that Go will execute, called test helper process, which if you look back matches this thing that it's wanting you to execute. We then guard it with an environmental variable that if it's not set, just returns. So if this environmental variable doesn't exist, the test always passes, so nothing happens. But if the envar exists, we actually do stuff. And the thing we do is actually look for that dash dash and reset the arguments to be whatever's after it. And then at this point down here, you can do whatever you want. You're now your own process that can do anything you want, that's no longer bound to the needs and wants of the Go test library, because OS exit 0 is going to halt the runtime right there. So the test, it'll never say the test passed or never pollute your standard out. You're your own person down here, and you can do anything you want. And so usually this is what I see. Usually arg0 is actually a sub command to run, and then the rest are the arguments, and you switch on it. So in our case, we have a bunch of different behavior we could exert on the helper process, like behave like something that after you start a process, accept the connection, just closes it. Behave like something that outputs some garbage on standard out when we're monitoring data for standard out. You could just change, you could, act like something that panics, act like something that exits with an exit code of this. You could affect all this behavior in the subprocess without actually mocking execcmd. You're actually allowing Go to actually subprocess code, and you're writing the behavior of that thing. So this is really good for mocking stuff that isn't overly complicated. Like you could never mock Git in here. That'd be impressive, but you're probably not going to do it. So like this is useful for other things. It's actually useful for Git if like you're just trying to make it do nothing, a no op or something. The important thing about all this is you need to configure your, one more back. You need to configure configurability, that previous section, because you need to be able to provide the execmd. So as an example, let's say you are mocking Git, and it's a Git downloader, so there's really no other reason that someone should be able to provide an execmd. Like maybe you make the configurable thing like the path to Git. It's not actually good enough if you want to do this. So you need to actually make it configurable with the execmd to actually use, and then modify that. And so that's an example of why configurability is so important. You could actually make subprocessing code untestable by not allowing me to send a custom execmd in there, or much harder. So make it configurable. All right. Okay, interfaces, sort of like almost done here, maybe a few more sections. Interfaces, so I should have included this earlier. This is actually kind of beginner. Interfaces are really important because they're mocking points. They're important for a lot of reasons, but in the realm of testing, they're important because they're points of mocking. With Go, you can't really, like in Ruby, you could just on the fly, any function, anywhere, sort of just rejigger its whole behavior. In Go, thankfully, you can't do that, but mocking points are a place where you could sneak it in. If your function's expecting an interface, and it's probably a file, like if you make the thing it's expecting an IO read-write closer, that usually is a file or a network connection. But you could actually pass in anything you want there and affect behavior. So it's similar to what I think about packages and functions, which is use interfaces a lot, but again, don't overdo it, and you'll figure out what that means. Anywhere you need a test where you need to affect a behavior that you can't do with configurability or something, then use an interface. So an example of where this is wrong is from before, is like netcon. So a lot of people view netcon as a mocking point, and it is. You can test things that way. I think the better way to test it is by actually making a connection. So you should do that, and that's the same view with every interface. Like any interface is a potential mocking point, but should you really mock it is a question that only you can answer. Okay, this testing as a public API is the next how to write testable code. This is something we started again in the past year of HashiCorp, and is actually probably my favorite thing that we've started doing in the past year. The idea is that you expose test helpers as an exported public API of your package. In HashiCorp, our practice is to have a testing.go and a testing_star.go if you need it. And _test.go, Go will ignore, right? That only gets compiled if you're in a test. But this doesn't follow. It's close. You can tell it has something to do with testing, but because we avoided that magic syntax, Go will include whatever's in here when you go get it, when you import it into another package, it includes it. And these include exported APIs for the sole purpose of providing test helpers for people that are using your package. And it allows other packages to test using your package and get mocks and get helpers and get functionality you're definitely going to need if you're testing something that uses your package without them having to rewrite it. So I'll give you examples of stuff that we actually use it for. So a config file parser. So for all our config file parsers, for Nomad, for Terraform, for Vault, we actually have testing.go that does stuff like this, which is test config t will actually return a complete valid configuration. And so if we change the config package to add a new field that is required, we could actually modify the config. If you expected a valid config, we could actually modify it to give you one. If you were using this as a test case in your own system that uses our config file format, and you were testing that valid files like don't fail your code, then our change to what is valid and what's not valid would actually trickle down and start failing your unit tests. And you might want that, but a lot of times you don't. And in this case, we actually are affecting your helpers that you're using for your tests to make sure that the behavior you expected isn't changing. Likewise, we usually include something like test config invalid that gives you an invalid config. And again, we could make sure that as long as you're using this helper, it remains invalid. That's a basic example. Here's another example, an API server. So Vault is the coolest one that uses this. We actually have test methods that return a server and a closer to end the server, and an address to access the server. And this will actually give you a fully in-memory configured server to use. So Vault core actually, or the Vault API package actually has a testing.go where if you were using Vault, you could actually, if your application is using Vault to encrypt data, you could actually start a fully in-memory real Vault server in your unit test without, which is pretty complicated. It's like this helper is like a couple hundred lines of code. It's not easy, but because of this, it's one line of code to actually get a fully functioning Vault server that you don't need to mock. You get it, it's in memory, there's no side effects, we guarantee that, and you could actually test Vault behavior. And this is important because we use this. We don't do this for charity. We use this in our command line and in our client testing packages. We actually, the command line test, unit test of Vault, when you actually run like the Vault read unit tests, are actually spinning up an in-memory, every unit test in our command line package is spinning up an in-memory Vault server, actually mounting backends, actually configuring it, running things, and then asserting output. And all that's a means to just asserting that standard out contains some text, but it makes the test really, really strong because it's not brittle in any way. I mean, it's real. Everything is real. If Vault's broken, then the CLI is broken, which is true anyway. So that's sort of a layered thing, which I talked about earlier, but also just incredibly powerful. Okay, another one is interfaces. This is my favorite practice that we've started doing. For interfaces, this is different. So this is test down, it doesn't return anything. The purpose of this is that if you have an interface, you usually expect interfaces to have a certain behavior. So for this library that downloads things, like this is the same library that uses Git. For this library that downloads things, every downloader, for example, if I ask it to download to a directory that doesn't exist, should create that directory and put it in that directory. Like that's behavior that every downloader should have. If I ask it to download something, if I asked it to download something into a certain directory, it should do it. Like that sort of stuff. And what we ended up doing is actually making a generic test downloader which wraps the common behavior that every interface should have and does it for you. So you give it your implementation of the interface and you give it the testing.t, and we test the common behavior because you probably don't know. The point when you do this and you're like, that's kind of cool, and the point that you are completely converted to this being your religion is when you find a really weird edge case and you add that edge case to the generic thing and help every implementation out there suddenly realize and fix this edge case. That's where it gets really cool. So we do this for a lot of things. Downloaders in particular have a lot of edge cases around paths and permissions and stuff like that. And it's really nice to find a bug, be able to add it to the abstract one, and see it fail in all our things without adding a test to each one and then fixing it. So there's that. as a corollary to dealing with interfaces, provide a mock. So you don't need to just provide functions, you could actually provide implementations. And so with all our interfaces, we actually provide mock interfaces out of our public testing API so that you could use that. And I said this, so that's fine. Okay, almost done. Custom frameworks. So Go test is a really incredible workflow tool. Like knowing that you just go test a package and everything's tested is really valuable. And we didn't want to throw that away for things that are difficult to test or not unit tests even. So what we've done in a lot of our projects is write custom frameworks you call from your Go test things to do complex things. So as an example, this is a real example copy and pasted from Vault. We have a in-memory acceptance test, but in-memory acceptance test framework for testing backends that store secrets and things like that. And it looks like this. It's very high level. You give it a pre-check function. You give it the backend that's being tested, which is just an interface. And then you give it a set of steps, which are some struct, which doesn't matter. And you give it a set of steps. And what, for example, this tests, we have a MySQL backend, which actually tests that if I configure all these things and ask for a password, I get something that I could then auth to MySQL to and not have access to these databases. Like, we could test that complex behavior that has a lot of boilerplate and has a lot of like intermediary things we have to do. Like, we have to set up a fully in-memory Vault server. Between each step, we need a new HTTP client. When we auth, we need to set the auth information on the HTTP client. We have to auth in general, which is actually complicated. So this lets you focus on, here are the things I'm testing, how to make the server, how to auth, how to do all that. That's not my problem. That's the test framework's problem. So this is just a custom harness for doing a bunch of stuff. Lets you just run Go test. So when you run Go test against something, it's actually doing something incredibly complicated, but what you're testing is really clear in there, and you don't have to learn how to do the incredibly complicated things. So people who contribute backends to Vault, which is very often, don't need to learn how to start up Vault, which is a pretty core thing that they don't need to know. They just write the tests, and they actually do write the tests because they're so easy to write the tests because we wrote a harness for them to do it that is still Go tests, so our CI just runs it, our developers just run it, it's easy. Okay, I think the last section, or one more, timing dependent tests. So timing dependent tests are pretty obvious. This is a timing dependent test. You are either waiting for something to happen or you're waiting for a timeout and then you fail because it timed out. Time-independent tests happen all the time in distributed systems. A lot of distributed systems are, please do a thing, but it's a network, so if it doesn't happen in a certain period of time, we assume it didn't do that thing. And so we don't use fake time. Fake time is a thing that exists in Go, but it's very, very common in things like Java. We don't use fake time where we control time. We actually use real time, but have multiplier configurations that allow us to change things. So if we're running it on our local laptops, or I have a desktop that I work on at home, like I don't need to change a multiplier because it's going to be pretty fast. When we run it in Travis, pretty slow, we'll set a multiplier of like 3. And so it's a pretty simple example, like make your timeout the timeout times the multiplier that's configurable somewhere, and then just do the normal thing. Fake time might be useful. We haven't been able to effectively use it yet. That doesn't mean we can't. Like a lot of the stuff I showed you today, we've only learned in the past year. So maybe if I gave this talk a year from now, it would be a big like use fake time instead. I don't know. But for now, I mean, we've gotten pretty far. We have 3 distributed systems or 4, and we've gotten pretty far with just multipliers as our test method. And then the last section, parallelization. It's really simple. So Go has this really nice thing that I thought was life-changing called t.parallel, where if you just do this somewhere in your test, it says that it can do other tests in parallel. So it's kind of weird how this works. I recommend you look at the source because I thought it was weird that how does it know this does anything? But basically at this point what it does is it spawns another Go routine to start running another test. And I thought this was great because I was like, oh, Ruby, when I worked in Ruby, suffered from this problem that as my project grew, the tests got so much slower, and you end up doing crazy, weird things to get them to run. And if I just throw this at the top of every test, all my problems are solved. 4 years later, it's within our company, it's a hard don't do it. If that line appears anywhere in our projects, remove it. We don't do it at all. We actually run multiple processes. So the main reason is because your unit test is now unit testing two things, which is it's unit testing that it works, and it's unit testing probabilistically that it works under parallel conditions. And usually you want your unit test to test one thing. And so when a test fails, it's not clear whether it failed because it actually failed or whether it failed because some other test is affecting state which caused it to fail in parallel. And for some people that feels like a feature, like you want it to fail either way because you want to know when this happens. But the way we've done that is actually write the things that happen in parallel, actually write another unit test that tests explicitly that when certain operations happen in parallel that they work because it's documented to work in parallel. Like if you say that something is thread safe, actually make a test that spins up two things, loops a million times doing operations and go routines on both of them, and then tests that the value is expected at the end. You should actually make that test. So you can simulate this yourself. Like if you insist on using t.parallel, at least run your test twice, one with parallel 1, so that line does nothing, and one with whatever you want to set the parallel to, at the very least. But we've chosen to just eliminate it entirely. I don't think it's that useful. And that's it. So thank you very much. I know that was a little bit long, but hopefully you learned something. So, thanks. And I don't know if we want to do questions, or I don't know. Aha. Yeah. Okay, he's nodding at me, so yeah.
I have a question about the slide with the test for the network connection. Can you go to that slide?
Yeah, let me use my computer to do that.
Thank you for the presentation.
Thanks. Thanks. Okay, what do you want to see? This one?
No, yeah, this one. Can you explain why there isn't a race condition?
Oh, yeah. Yeah. There probably is a race condition. I do always protect against race condition. In the interest of space, I didn't. But in my head, when I wrote the slide, I was like, maybe not, because the way TCP works is that the connection has to be fully established before it returns. It is possible that it's fully established, but not yet written to this variable. So that's probably the race. But in general, what I do, I had it and I deleted it. It actually fits on this slide. It just makes it a lot more complicated. Is have a channel that you close when you defer close the channel, and then just wait for it right there. That's it. Any other questions? Yes. I almost pointed the laser pointer at you. That would have been a mistake. Yeah.
I think it's a really great idea to use fixtures for all files you're using in your workflow, and also the golden files. My question is, and I've been wanting to do that a lot with testing, but I was hesitating because I was afraid that it would slow down my tests too much to work with real files and not buffered I/O. Especially due to all the syscalls, you have separate operating systems, and just the fact that reading from disk could be really slow. What impact does it have on your tests?
If anyone can hear the question, is like, what performance impact does test fixtures have on your test? I'm sure in the world of computer time, a massive impact, but in the world of human time, an unnoticeable impact. So it probably makes your tests go from microseconds to nanoseconds are bigger, right? So nanoseconds. But you know, it makes it go to the bigger one. But for a human, it's not noticeable. So as an example, like the config, I use it a lot for config, where config packages, the test fixtures are like 50, but like Terraform's case, hundreds of fake configurations to make sure that it parses them properly and generates the right structures. And it's still a test package that go test finishes in like 0.03 seconds. You know, files are fast. Syscalls at that layer are fast. Like it's not noticeable. Yeah. In most times, like what you're testing, what you're running is probably slower than the files loading. And if files are actually slow, you could probably do a bunch of like weird hacks to actually preload them in parallel, like into the init function while other tests are loading, and crazy stuff, but I don't think you'll need it. Any other questions? Yep.
So the timing thing was interesting. In my experience, because Go has this whole concurrency thing, timing is very often an issue to test it. There was a bit anticlimactic to just see the scale up of the time. Because, I mean, I'm running to this quite often. I said, like, okay, a second is certainly enough for that, but then people run it on their crappy AWS instance or in a crappy CI environment, and the test fails because 1 second was not enough.
Okay.
So now I can just tell them, just scale.
No, I could give you a better answer. I should have written this down in the slide. The best timing sensitive test to have is to actually be able to control that behavior and not have a timeout at all. So for example, and I will admit that we haven't solved timing. So like Consul unit tests, for example, still fail in Travis, which is incredibly annoying to me, but I'd rather like work on things that matter more than have the Travis test specifically for Consul pass when they test when they pass on our laptops before we release. Like it's less important for me, but but in Consul, a good example is we have a test util, like a public test API thing, and one of the test functions in the thing is wait until leader. So we used to before start like 3 Consul instances in memory and naive test of leader election. We'd start 3, time not sleep 300 milliseconds, and then check if there's a leader. And so that's basically the same of saying like, wait until there's a leader or after 300 milliseconds fail. It's the same. We didn't do it like the select, which would have been nice, but we did it serially, but it's basically the same thing. And the better way to do that is to not have a timeout at all and actually just wait for the leader to happen and have a much longer timeout, like a 10-second timeout when it's probably going to take hundreds of milliseconds. And the way we did that was actually hook into the core of Terraform that under tests actually emits on a channel once it's elected a leader. So instead of just being like start up 3 and wait, we actually just select on a channel until there's a leader, and then have the timeout, which still exists, just be way longer because it's probably not going to hit the timeout. So.
I'm glad to say that, because I was finding myself writing exactly those functions that are only used in tests, wait for Q ratio to happen or something. And you think I'm lazy, I don't have to write that. But apparently it's the only thing.
Yeah.
Work on Travis in the end.
Yeah, and the other thing I guess I could have included here in a writing testable code or writing debuggable code was how I categorize this, is only in the past few months, this is a much newer thing for us. We've started making every potential point in the code that could be slow, we wrap it, like block and hang the program. We actually wrap it in a function that does go routines the potentially blocking thing, and then puts a timer, and if it exceeds a certain time, just logs a message. And the reason is because like when you run a test, or really this even logs in production, like if you run something and the thing is hanging, there's hundreds of thousands of lines of code where it could be hanging, and you don't know why. And for Terraform especially, it's important, this is where most of it exists. It's like, it's nice when in the debug logs, you actually start seeing a ticker every 10 seconds. It's like, nope, I'm still doing this thing. Like, it's still happening, don't worry, everything's still working, versus if you don't see anything in the logs, it's like something is well and truly screwed somewhere. And so that's another way to do it, which doesn't affect tests, but at least helps debuggability, where a hang doesn't become like, is it a go routine hang, is it a network hang, is it a file open hang, is it a file write hang? Like, you don't know where it is. Now you have a log message that's going to tell you at every point where it could hang. Yep. Any other questions? Yep.
I have one global question. You mentioned that you called it Ruby before.
Okay.
And I understand that Go is better from the terms of performance. But
Yes.
if you just think about what language do you like and not thinking about performance, then will it be Ruby or Go?
It could be a controversial question. A trait of me, I'm not saying this is a truth in the world, a trait of me is that I actually like compiled languages better. I like typed languages better, and the Rust person in the room is going to like yell blasphemy and be like, Go is not typed, but it's fine. I like languages that, basically the way I describe typed languages, so the reason I have an opinion on this is I actually have a bet with my co-founder, Armand, who also wrote almost everything up here. He likes dynamic languages better. He won't use them because we do believe Go is the right choice right now, but we have a bet where It's a 40-year bet. It's in my calendar with an alert. Like if I'm alive in 40 years and he's alive, I will call him out on it. It's a bet where I think that statically typed languages will win, and I'll define win in a second, and he thinks that dynamic languages will win. And the definition for win is that languages will have a distinct compile phase and runtime phase, and as part of the compile phase, you can get an error that has a type error, is the definition for win. And so mine is more constrained than his, but I think that I like static language, so I would still use something like Go. And after 4 years of Go, I could actually write Go fast enough that even though it's compiled, like I could prototype something really fast in Go. So it's fine. Anything else? But I've already done the work, so your 4 years is not my problem. Any other questions? Yeah.
Apart from the parallel thing that you talked about, were there any other features, either the expanded library or any third-party libraries which seemed like a really good idea, and then a few months later it turned out to be a fucking terrible idea?
Yeah, is there anything else that I thought was a good idea and now is a bad idea? I mean, netcon mocking, all the stuff I learned up here. I thought there was something else that was a better idea. I'm sure there's stuff on here that I think is a good idea that won't be in a couple years, but I don't know. Yeah. You learn through some sort of pain. Anything else? Cool, thank you.
So, thank you, Richard. Thank you very much for this interesting talk. We did record this talk and we'll publish it very soon on our YouTube channel, which is New Tech Berlin, right? So if you haven't mentioned our tech talks or retweeted some of the tweets we posted, please do that. NewStore Tech Talks Twitter account, mention New Tech Berlin, and you can get a goodie bag afterwards. Yeah, there's some beer left, some pizza left, so we can all meet outside for another chat for some minutes for beer. And as mentioned, we planned 2 very interesting talks in April. We have Greg Kirstians speaking about Postgres, and in May, Sao Chong will speak about Go. Yeah, so see you soon here again. Thank you very much. Bye.